Hey guys, welcome to our channel of Sciences and Mathematics. Our discussion for today is going to be the broader topic of energy changes in physical and chemical processes, and that is the concept of enthalpy of neutralization. Now, this process of neutralization is chemical reactions that we learn about. So it's basically entails an acid-base reaction, as we're going to see perhaps by example. But in this process, we're going to look at the concept of heat that we've already talked in some of our videos and try to see how we can be able to measure the enthalpy of neutralization of a specific reaction. So without further ado, thank you and welcome. So as I've said, our topic for discussion for today is enthalpy of neutralization. And as I've mentioned, neutralization is a process that entails the concept of a reaction between an acid base, which results in the formation of a salt and water. Now, from the term neutral, from our pH scale, the concept of a pH scale, you know that this is going to form a compound which is basically a neutral compound. So therefore, we're going to see the energy that is involved. Now, in our case, this particular discussion is special in a way, because as we said, we have a formula for finding the enthalpy change, which is given as MC change in T. So in this case, we're going to see that there is a variation in mass, as we have already looked at this in different videos. In this specific reaction, we're going to have two specific substances which are reacting, therefore changing their net volume, that is 50 centimeters plus 50. So in my setup, which I've just given in for demonstration purposes and the sample results, we are having 2 molar sodium hydroxide that is being mixed with 50 centimeter cubed of 2 molar HCl. So basically an acid-base reaction will of course give us this concept of neutralization. And in the setup we have a tissue paper, basically which is trying to act as an insulator, as we are trying to measure the temperature so that it's not affected by the surrounding environment. And we are also going to see that in this neutralization reaction, this specific sodium hydroxide and HCl have different temperatures. So when we mix before the reaction, it will be appropriate for us to try and find out what is the initial temperature. So therefore, because it's two liquids reacting together with different temperatures, we'll take an average of those temperatures as our initial temperature, and that is the one that we are going to use against the final measure of the temperature of the reaction. So in this case, as I've said, we have sodium hydroxide reacting with HCl. So we can have a stoichiometric equation for sodium hydroxide reacting with the HCl to form sodium chloride plus water. So this one is stoichiometric. So therefore, the reacting mole ratios for this specific reactants product is 1:1. So basically, I've said about the concept of temperature, and as I've said, the initial temperature reading that will be taken is the average of the two particular reacting species, that is for sodium hydroxide and HCl, and then we find an average. So my table at this lower right side of the table, the board, consists of a temperature of HCl and sodium hydroxide, given as T1 for HCl and T2 for sodium hydroxide. And then we're going to find the average for this particular two. So this initial reading is the one that is going to give us the initial temperature. And in this case, of course, after the neutralization process was over, the final temperature was recorded to be 35. So we're going to try and find out how we can be able to calculate the molar enthalpy of neutralization. So therefore, from this case, we can be able to try and calculate the change in temperature, which was the final temperature final minus temperature initial. It's going to give us the change in temperature. So you can just maybe pick up the readings from this particular case so that we can be able to use that particular space. So we have temperature final as 35 minus temperature initial as 25.5. So this is going to give us the difference of that is 9.5. I'm right in my calculation, this is 9.5 degrees centigrade. So that is going to give us that the difference in temperature. So the final volume of the resulting solution is a mixture between sodium hydroxide and HCl. 50 centimeters plus 50 is going to give us a volume. So the volume of solution, the final solution which is making up the product, is 50 plus 50 for HCl and sodium hydroxide, which is 100 centimeter cubed. So we said that when we are trying to find the molar, the enthalpy change, we use the density for water. So basically we are going to assume that that specific solution has a density for water. Therefore, in trying to find mass, we're going to find that this is equivalent in 1 gram per centimeter cube as the density of water. For 100 centimeters cubed, this is going to give us 100 grams, which is equivalent to 0.1 kilograms. So therefore that is going to form our mass. And then we're going to use the specific heat capacity still for water, which we said is the value for C is 4.2 kilojoules per kilogram per Kelvin. So therefore that is what we're going to use. And the change in temperature, of course, we have given it as 9.5. Therefore, our change in enthalpy is going to be mass 0.1 kgs times specific heat capacity 4.2 kilojoules per kilogram per Kelvin, and then this one we multiply it times the temperature change. We said that the temperature change can be degrees or centigrade, but the absolute value is going still to be in kelvins. So therefore we just have these specific units given as such. So the product for this is going to be 3.99 kilojoules. So therefore that is the amount of heat that is involved in that case. So suppose we are asked to find the molar heat that is evolved, we can be able to use this one and the stoichiometry over this particular equation and trying to find out what is the amount of heat that can be used for 1 mole. Now that we have been given, so I'm going to have this, maybe this value just indicated somewhere for memory. So this is 3.99 kilojoules. So using these specific concentrations that we have been given for the acid and base respectively, we can be able to find the amount of heat or the molar heat that is involved in this particular reaction. So therefore we are going to add the number of moles of acid. Now for the acid, 2 moles are contained in 1,000 centimeter cubed. It is 50 centimeter cubed, the acid that was used, so maybe X number of moles will be equivalent to 2 times 50 divided by 1,000, which is basically 0.1 moles. So 0.1 moles that were used. Therefore, we can say that 0.1 mole evolved this specific value, 3.99 kilojoules of heat. Therefore, 1 mole will be equivalent to that 9.9 kilojoules per mole. So that's how we can be able to find the molar heat that is evolved in that specific kind of reaction. And still we can be able to go ahead and try to demonstrate some of the concepts that we have already discussed, especially pertaining to the ionic equation for this neutralization reaction and the thermochemical equation that is involving, of course, this heat that is evolved during this reaction. So this is 39.9 kgs, and the difference in temperature, there was an increase in temperature, which basically implies that heat was taken away from the system to the surrounding. So therefore, we can write an ionic equation for the neutralization reaction, which was an acid-base reaction that resulted in the formation of water. So this is ions. So therefore, we're going to have an ionic equation represented as such. So if we were to write a stoichiometric equation or maybe a thermochemical equation using this ionic equation, we just write H aqueous, OH negative aqueous, forming a liquid, and then we have enthalpy change. This is negative 39.9 kilojoules. So we are going to have that one given as, so this is kilojoules per mole. So that's going to form a unique equation for that. So this basically entails the concept of enthalpy of neutralization, and the molar heat of neutralization that we have found a value for, that 9.9 kilojoules per mole, is the enthalpy change that takes place when 1 mole of hydrogen ions from an acid are completely hydrolyzed by an acid from an alkali, or maybe from a base. So that is it for this particular discussion. Of course, we have seen that it has a relationship with some of the videos that we have already talked about, the enthalpy of formation and the enthalpy of course, we have talked about the enthalpy of formation, enthalpy of substitution, whereby the copper and the zinc ions were involved. Now, in this case, there's a difference in that by joining these particular volumes together, we are forming a different volume, which is 100 centimeter cube, therefore, which is going to play a role in the mass of that specific heat enthalpy. So therefore, I think this is it for enthalpy of neutralization. And perhaps we're going to do some more examples in our practice questions so that we can be able to acquaint ourselves on how we, or maybe get familiar on how we can deal with questions which pertain to the molar enthalpy or enthalpy of neutralization. So that is it for this discussion. Bye. God bless you.